All right, folks, we're about halfway through day 04 structures. This should be a quick one. We're going to talk about pairs, also called tuples. Pairs are a super simple structure. You have two things. That's it. That's that's the tweet. So what does that mean? So here's the type. We'll call it prod for product, named after a Cartesian product, named after Rene Descartes, who invented the idea of this sort of like the Cartesian plane, right? Like that grid is about a pair of numbers to sort of codify 2D space. So in general, this idea of combining two number lines, two products, taking two things together like that, is called the Cartesian product in his honor. He was a boss. He was a weird dude. Um, and there's one constructor in this type. Kind of interesting. I think this is the first type we've met with only one constructor. It's a type that takes two parameters because the two different parts of your pair could be different types. Right? You could have a pair of a bool and a gnat, or a base and a day, whatever. It's cool. You could, of course, have pairs of compound types too. You could have a pair of a list of gnats and, I don't know, a boolean. Okay, so the singular constructor we have here is called pair, and it takes something of the first type and then something of the second type. So a couple of things are really going to help us here in terms of like making this usable. So first, we don't want to ever name these types X and Y. Great. Next, we want to have this tuple notation. This is really common in mathematics. Like you've seen points, like on the XY plane, you'll write like 0, 0. That's the origin, right? We wanted prod nat nat. That's going to be right now. Okay, this is the origin, but it's a little funny. This is the origin for like, do I have this right for you? No, for this, right? It's very hard to do mirror images. This is the top, only the top right quadrant, positive, positive, right? Fine. Okay, and then the conventional math notation for these product types is to use star or to use an X symbol. We'll use this multiplication symbol, which I think we've seen once or twice in error messages so far. So we can actually do one better. There's one origin. Here's another one. Woo, can't type. Origin, nat times nat. Nat times nat. Beautiful. Okay, this annotation type scope is a way of sort of telling Coq where this lives. You don't need to know about this stuff, but it's a thing. It is important to not get these two things confused. This, that what I have highlighted now, x times y, that's a type. This x comma y, that's a pair of types. Right? In some languages, these are punned, where this is how you write the type of pairs. That's not how you do it in Coq. So we can write some useful functions, right? These are just like handy things. So the function fst stands for first, and it gets the first element out of a pair. It takes something of type x times y and gives back x. SND, that's second, that takes a function of a value of type x times y and returns the second thing, y. Right? And it's funny maybe for you to see these matches that have only one clause, but like, okay, why not? All right, there's one exercise here, and it's an important functional programming concept that's a little bit hard to get your wrap your head around. Basically, in Coq, you've noticed that a function that takes two arguments has type A arrow B arrow C, and we've said that's right associative. That's really A arrow B arrow C. Right, so if you give f a value of type A, then it gives you back some other function f prime of type B arrow C, where f prime knows something about the A value you gave it. If you give f prime some appropriate B value, you'll get C back. Right, this allows for partial application like we saw, where you like do plus 3, and then now you have a function that adds 3. So this notion of like treating a list of arguments as iterated functions is called currying, in honor of the logician Haskell Curry. You may have heard of the programming language Haskell or the delicious dish curry. Now, in many languages you might have seen, they don't work this way. Instead, you have to always give all of your arguments at once. One of the languages you might have seen that does this is math. In math, if we're going to define a function, you'll say, okay, here's a function f that takes two naturals, right? And it's going to return another natural. F of xy is 2 times x plus y. Okay, cool. Now the math notation has you taking both x and y at the same time. You can think of it as taking a pair of things, and then it returns a single thing. You could write it differently, though I will not be held responsible for the way your math teachers treat you if you write it this way. So f prime, a different version of the same function, says, no, no, no. You give me the first argument x, and I'll give you a new function. F prime will return g sub x of y, where that sub x is a way of, like, you write a little subscript, maybe you've seen this before, that says this is the g that remembers x, right? You're sort of like holding on to that second argument. Okay, what does g sub x do? Well, it's a nat or nat function, and it just takes y, and then it returns 2 times x plus y. So this is a sort of curried math function. So if we wanted to do f20 and 7, okay, f27, that gets us to this sort of, you know, patriotic is the wrong word. What do you call it? School pride-ish answer? Chirp, chirp. F prime of 20, that just gets us to G20. G20 applied to 7, okay, that gets us back to the mysterious number 47. So functional programmings like Galena, they're going to use curried function application. It works really well for the sort of function-oriented programming style that we inhabit here. Other programming languages tend to use uncurried functions. Now, it turns out these are totally equivalent views. Haskell Curry was the first person to really notice this. So we can write a function, and this is where it gets really weird. We can write a function that takes an uncurried function, something that takes its x and y arguments to return z all in one go, and turn it into a function that takes x, and then takes y, and then returns a z, by just sort of waiting and then applying it. So you have an exercise to write the opposite. Given a function that takes x, and then y, and then z, take in a pair of x and y and do it all at once. All at once. Pardon me. Okay, and we can check the types of these things. So just to see, so Curry says, give me an x times y arrow z function, and I'll give you an x arrow y arrow z function. Uncurry goes the other way. Give me an x arrow y arrow z function, I'll give you an x times y arrow z function. Right? These two views are sort of equivalent. A thing that we'll be able to prove later on is that these two form an isomorphism, right? That they are inverses of each other. Okay, that's about all we're going to say about pairs for now. Pairs will come up on and off. It's super useful to be able to talk about holding more than one thing at a time, or even more than that, because you can, of course, nest pairs, right? You can talk about things like, right, this is a pair where the right-hand value is itself a pair. So this isn't quite as good as lists, right? Lists are unbounded. A list, you could have any length. Here, the type of a pair tells you how many things you're actually going to have, which is actually useful. Sometimes it's nice to know you only have a finite number of things. Okay, so much for pairs. We've got a couple more data structures to do, and then we'll talk about drawing data structures. Getting in close. We're almost done. All right, cheers, y'all.